Hello, Calculus and Vectors class. We're going to deal with calculating limits today. In the last couple of lessons, we talked more conceptually about how limits work and how to determine if there is a limit and if it's continuous, and looking at a graph, how that all works. In this one, we're going to focus more on the algebraic side. And by the end of this lesson, you should be able to calculate limits of functions from their formulas using the properties of limits. And you should be able to calculate limits involving the indeterminate form of 0 over 0 and a couple of others, which we'll talk about a bit more after. This first section here is a review from the last lesson, so if you're not sure about that, check out 4.4, but we're going to skip ahead just to keep this brief. Normally this next section I'd have you guys do in pairs just to get a bit of practice with these. But essentially the big takeaway from this is that when you look at these functions, y equals 5 or y equals square root of 2x plus 5, what you should discover is that if the function is continuous, we know that the limit's the same as the function value. So instead of limit of x approaches 1, x approaches 1, it's just going to be the same as f of 1. This is just going to be the same as f of 3. So all you have to do, generally speaking, is plug in whatever x is in your limit definition into the function, and it should give you that. So for the first one, it's just x equals 5, and then for the second one, it's f of 3, which is the square root of 2 times 3 plus 5, which is square root of 11. Now, by the way, just so there's no confusion here, I changed to a positive 3. I always forget to change it in my lessons, so it was never meant to be a negative, so there's no real trick around that. I just had a typo, so don't worry about that too much. Now, dealing with the third problem here, this is a rational function. We've worked those before, and we know that looking at this denominator, we have x minus 2, which means that we should have an asymptote at x equals 2. So if we're looking at the limit at x as x approaches 2, we're not quite sure what to do here because there's an asymptote. We dealt with that a little bit graphically, but we want to see if we have better methods for that. So we're going to stick a pin in that for right now. Let's learn some algebraic methods to help us out, and maybe they can help us out a bit. So I've listed the 9 big properties for limits. I'm not going to go through in too much detail here, but just have a read through these, and they should just give you a few more tricks for helping with calculating limits if you're ever stuck. Now that we have those, let's talk really quickly about some of these problems again and use those rules to help us, because we like using more algebraic methods because they're a bit more exact. So the first problem, the limit as x approaches 1 of 5, we said it was going to be 5, but looking at our limit rules, we said that lines up with rule 1. The limit as x approaches a of a constant is going to be the constant. As it turns out, it doesn't just work for that one, it works for any constant. If you have a constant inside your limits as your function, then it's just going to be the constant again. For the second one, and again, we're going to change that over to positive 3 because I keep forgetting to change that over. That one connects in, we could use rule 9 to help us with that one. Now rule 9 says that if we have a limit of a function that's inside a radical, we can take the limit of the function inside the radical and then put it underneath the radical. So we can rewrite this as the limit, as the square root of the limit as x approaches 3 of 2x plus 5. So that would just be the limit, or the square root of 2 times 3 plus 5, or square root of 11. So notice with these rules, the calculations don't really change very much. It's essentially the same thing, but there are going to be some situations where they might come in handy, so they're good to know anyways. Now, dealing with this one here, with problem 3, we have the limit as x approaches 2 of 5x over x minus 2. And with this one, you're going to notice that the one that most closely relates to this, there's rule 7, which deals with division or fraction or rational limits. Now we could rewrite this as the limit as x approaches 2 of 5x over the limit as x approaches 2 of x minus 2. But you're going to start to notice a big problem here. On the bottom, we're still dividing by 0, which according to rule 7 is a big no-no. So we can't do that. So in this case, we're going to have 10 over 0. So we're still a little bit stuck here. So as a general rule, use the algebraic methods. Those are our best option because they're the most mathematical and they're going to give us the most accurate result. If we can't do that, then we're going to start dealing with our graphical forms and using less exact methods to help us. So let's deal with that same problem again down here. In this case, if we can't use the limit rules, what we're going to do is we're going to start using our knowledge of left-handed and right-handed limits instead. So let's take a look at the left-handed and right-handed limits for this one. So the limit as x approaches 2 from the left of 5x over x minus 2, and the limit as x approaches 2 from the right of 5x over x minus 2. And we could use that same trick before where we just pick a number just to the left or just to the right to help us out. To the left, we could pick maybe, let's say, we could plug in 1.999999 into our calculators and use that to help us. And we get a number that is very big but negative, which leads us to believe that from the left, we're approaching negative infinity. We can repeat that for the right side of our function. So we could pick a number just to the right of 2, which could be 2.0000001. We punch that into the calculator with our formula. It'd be 5 times 2.0000001 over 2.0000001 minus 2. And you should get a very big positive number if you do that. So now looking at the left-handed and right-handed limits, we have negative infinity and positive infinity. But we said that for a limit to exist, they have to approach the same value. So in this case, they're totally different. So in this case, therefore, the limit does not exist. Let's take a look at a different one, just so we have a bit more context here and you guys see something a little bit different this time. So in this case, with the limit as x approaches 4 of 1 over x minus 4 squared, we know if we evaluated that, that would be something like 1 over 0. So again, it's in that form 1 over 0. And by the way, I didn't mention that was not 1 over 0 in the last one, it was 10 over 0. But it's really, and when we say 1 over 0, it's anything in the form a over 0. It could be any value up top, except for can I be equal to 0. We'll deal with that case in a little bit. So in this case, we have 1 over 0 when we evaluate it, so we don't really know how to work with that. So again, we're going to use left-handed and right-hand limits to help us out a bit. So let's look at the limit as x approaches 4 from the left of 1 over x minus 4 squared. And then we're going to look at the limit as x approaches 4 from the right of 1 over x minus 4 squared. And you should hopefully notice with this, it doesn't really matter what's going to happen. As you punch these in, we're going to pick two numbers that are just to the left and just to the right. So we could pick something like 3.9999 and put a whole bunch of 9s in there. Then we could do 4.0001. just going to punch them into the calculator. And for the left-handed limits, if you punch in 3.999999, however many nines you like, the more he can get in, the better. You should get a very big positive number for this one, because we know that we're going to be, if we subtract 4 from that 3.999, we're going to get something very close to 0. And if we square it, it gets even closer to 0. So it's 1 over a very small number, which becomes a very big number. When we look at the right-handed limits, we get the same thing. We get positive infinity. So in this case, because the left-hand and right-hand limits both approach infinity, we can say, therefore, the limit as x approaches 4 of 1 over x minus 4 squared is equal to positive infinity. Or we could write just infinity, but positive infinity is equally correct. Let's continue on. Let's do a couple more. So again, we said our first method is just trying to plug in the number and see if it works for us. So if it gives us a result, then we're happy. So in this case, we could actually break this up. We could use that subtraction rule, which was rule 4, to help us out, and we could divide it up. But if we can just plug in the number, we know that this is a quartic function, so we know that we could just plug in the number, and it's continuous anyways, so we don't have to. So we're just going to do that. So 3 times 2 to the 4 minus 5 times 2 is going to be 3 times 16 minus 10, which is 48 minus 10, which is 38. For the next one, that's going to be negative 1 squared minus 4 over negative 1 squared plus 3. And again, as long as we don't have a 0 on the bottom, then we're fine. Let's just double check, make sure. So that's going to be 1 minus 4 and 1 plus 3. That's going to be negative 3 over 4. So again, just to reiterate, if you could just plug in the numbers and solve, then generally speaking, that's fine. If you need to use your limit rules that we listed on the last page, then those are the next step. And if you get something weird like 1 over 0, then we can examine the left-hand and right-hand limits. So those are our 3 methods for right now. So let's try this one and see what happens. So this one, as long as we don't get something weird, then we should be okay. Let's plug in the numbers and see what happens. That's going to be 1 squared minus 6 times 1 plus 5 over 1 squared plus 1 minus 2. So in this case, we get 1 minus 6 plus 5, 1 plus 1 minus 2, which is equal to 0 over 0. Okay, so this is something we haven't seen before. We've seen limits that work out to a real number. We've seen limits in the form 1 over 0 or a over 0, but we couldn't have the top part being 0. This is something new. So right now we're not sure what to do with this. So we're going to learn one last trick about limits that's going to help us a bit. So, well, it's actually a few tricks, but they're all kind of rolled into one. So we're going to learn about something called indeterminate forms. Indeterminate forms. Now, what that means is basically we have an indeterminate form whenever we have 2 rules that are conflicting with each other and giving us different information. In this case, when we talk about 0 over 0, we have a few rules. We know that the top 0 is like multiplying by 0. We know that normally if we had 0 over any number, it would be 0. We know normally that if we had any number divided by 0, it would go towards either positive or negative infinity. it would approach that, because we know that that's what happens when we have something over 0. We looked at that with our a over 0 examples a little while ago. So now we have two rules that conflict and are giving us different information. So as it turns out, with these ones, it's going to be somewhere between 0 and positive and negative infinity. So as it turns out, in a lot of cases, we can actually use a bit of math to help us out. We won't go through all of these and explain why these are indeterminate forms, but I'll give you one more example here. So with 0 to the power of 0, we know that if we had 0 to the power of some number, usually it would be 0. We know that if we had some number to the power of 0, normally it would be 1. So in this case, if we had 0 to the power of 0, it would be somewhere in between 0 and 1, and we're not quite sure where. So in these cases, there's a few methods that we can use. We could use factoring. We could use rationalizing the numerator denominator. Don't worry if you don't remember that. We'll talk about it really quickly. And we could use expanding and simplifying to help simplify what we're looking at. So depending on the problem, we're going to use whatever methods make the most sense. So with this first example, you can go through and do the calculations. You can plug in 1 if you want, but I'll tell you this ends up in the form 0 over 0. So this is an indeterminate form. But you'll also notice that we have two quadratics. So to help us out here, let's simplify this a little bit and let's factor. So we're going to do equals x at the limit as x approaches 1. Now, just be careful here. Sometimes people will put the equals sign after the limits. I see this in calculus assignments all the time. So the limit's kind of like an operation. So just like absolute value, you wouldn't try and mix the equal sign into it. So keep the equal sign to the left of your limits always. So for this one, let's take a look up top. We can factor this, and that would look like x minus 5, x minus 1. On the bottom, that's going to be, if we factor, it should be x plus 2, x minus 1. And you notice here, we have two terms that cancel. Or sorry, two sets of brackets that cancel. So the x minus 1s up top and on the bottom, they cancel out, and we're left with the limit as x approaches 1 of x minus 5 over x minus 2, which is just equal to 1 minus 5 over 1 minus 2, which is equal to negative 4 over 3. So isn't that interesting? We actually just found another way to work around that whole dividing by 0 problem. That might come in handy a little bit later when we go back to rates of change. Let's try a different one. So in this case, we have the limit as x approaches 1 of 1 plus x squared minus 4 over x minus 1. And we know that 1 minus 1 is going to be 0, so our denominator is going to work out to be 0. And I'll tell you, that's going to, up top, it's going to be 2 squared minus 4, so 4 minus 4 is 0. So again, that's going to be 0 minus 0. So again, let's use a bit of algebra to help us out. So up top, that looks like we can probably simplify that a little bit. So let's expand up top. 1 plus x squared is going to be 1 plus 2x plus x squared plus 4 over x minus 1. So we combine the like terms up top, and it's going to be x squared plus 2x plus 5, minus, whoops. That should have been minus 4. Which would make this x squared plus 2x minus 3 over x minus 1. And again, it doesn't look like it's helping us too much, but now you notice that we have quadratic up top. So let's try and factor that and see what happens. When we factor that, we get x plus 3, x minus 1. all over x minus 1. So now we have x minus 1 up top, x minus 1 on the bottom. We can cancel those, and it just becomes the limit as x approaches 1 of x plus 3, which is just equal to x is 1, so 1 plus 3 is 4. Now, just before we leave this, I'm going to give you one more example, just because we didn't talk about rationalizing. Now, I'm sure you guys dealt with this in grade 11, most of you, just to help us out. So we're going to do one more example here. The limit as x approaches 0 of root 16 plus x minus 4 over x. Now this one looks a little bizarre, but we're going to use a little knowledge that we dealt with last year. And think back, we talked about conjugate pairs. So conjugate pairs just means when we have a rational up top, if we have a minus sign, we're going to make it a plus sign. If we have a plus sign, we're going to make it a minus sign. So hopefully you remember that from grade 11, your 3U math. So we're going to multiply by the expression up top with the square root, but we're going to take its conjugate pair. So instead of minus, we're going to do plus 4. And then we're going to divide by the same thing to keep it equal. So that way it's 1 over 1. And what you're going to notice here is that up top, let's take a look. We notice that's actually a difference of squares. So we could actually say that is the same as saying root 16x plus x squared minus 4 squared. All over x times root 16 plus x plus 4 times x. So then up top, let's simplify that a bit. The square root and the square cancel, and we're left with 16 plus x minus 16 all over x times root 16 plus x plus 4. And hey, look, we have a 16 and a minus 16, so those are going to cancel. That's going to be x over x times root 16 plus x plus 4. And hey, look, now we have an x up top, x on the bottom. Those can cancel. That's going to be the limit as x approaches 0 of, that's going to be 1 over 1. So that's going to be 1 over root 16 plus x plus 4. And now we have this form here, and now the bottom is not going to be 0 anymore, so we can just plug in 0 for x, and that's going to be root 16 plus 0 plus 4, which is equal to root 16 is 4 plus 4, which is 1 over 8. So that knowledge that you used last year from conjugate pairs can actually be used here to help out a little bit too. So just to quickly summarize, with limits, always start with your basic limit rules and try and plug in. If that doesn't work, let's say if you get 1 over 0 or some sort of a over 0 that's not 0 over 0, then you can use left-hand or right-hand limits. And then if you get an indeterminate form like 0 over 0 or 0 to the power of 0, then start using algebraic methods like FOIL or expanding and simplifying or factoring or conjugate pairs to help you a little bit. Okay, so that's pretty much it for a quick look at limits. Do the practice, make sure that you're good with these, because once we go back to calculus in the next lesson, then we're going to start taking this and putting it into calculus to help us solve problems in a way that's a bit more algebraic and a bit more exact. So happy practicing, and don't forget to wash your hands.